Okay, good afternoon or good morning to everyone who's joining us for this week's InfoSystem Teixeira Random Geometry Colloquium. Today, we're very glad to have Augusto from IMPA, who is now in a sabbatical at University of Lisbon, who will give a talk on percolation on randomly stretched lattices. Over to you, Augusto.
Thank you very much. Thanks for the invitation. It's always a pleasure. Of course, last time I spoke to an audience in India, it was in person, which is always better, but it's also a very big pleasure online. Sorry, I missed the date. I'm still in 2022 somehow. I'm catching up. So this talk is going to be based in a joint work with Marcelo Hilario, Marco Sá, and Remy Sanchis. So I'll start very slowly, giving an introduction to percolation itself. Sorry, I have two devices here. There we go. So percolation as the simplest model of phase transition we know, one of the simplest maybe. And then we are going to talk not exactly about the standard percolation model, we're going to talk about a modification of it. So that's what I'm going to introduce later, the columnar defects issue. And then I'm going to give some classical theorems and go through a little bit some of the proof ideas and the takeaways from those. So please stop me at any time. It's supposed to be a slow talk and hopefully even end before time. So I think it's very good if it's an interactive and ping pong type of talk. Okay, so percolation, the original model was introduced by Broadbent and Ramsley in '57. It's, as I said, one of the simplest models that feature an interesting phase transition. Has been studied extensively, many things about it, and there are also many things we don't know about it. From the physical part, everything is basically understood. At least that's what I understood from the physicists. But as you go to the math part, there are still deep open questions which basically come from the physics. We're going to introduce the model in 2 dimensions because that's mainly what the talk is going to revolve around. So fix Z2 and add edges to nearest neighbors. So now you have a square grid. And for each of these edges, you're going to kill it with probability 1 minus p and retain it with probability p. So this is a parameter that we fixed beforehand between 0 and 1. And we do this independently for every edge. And what we get in the end is pictured here in this simulation. It's just a random subset of Z2. And the type of questions that we're going to ask about it are connectivity questions. So let's take a very particular one, but that's a representative question. Is the origin connected with infinite? So is there an infinite path, self-avoiding path from the origin that only crosses open edges? So this is the event that we're going to focus for this first part. And it's a monotone event in P. So if we open more edges and the thing happens, the thing is also going to happen. And we are going to denote this probability by theta of P. And this is what we could call order parameters from the physics. It's what we are, it's a simple real quantity that kind of represents an aspect of the physics we're interested in. And as I said, it undergoes a phase transition. What does that mean? There's a beautiful and simple counting argument by Peres that shows that if you take p small enough, say smaller than 1/3, then this function is 0. So it's 0 in a whole interval. If it was analytic, it would be 0 everywhere. But what we can also show with Peres' argument is that for p close enough to 1, say it's bigger than 2/3, it's positive. So there is some point in between where you're losing analyticity. Here we can see a plot of what one expects this function to look like. So it's expected that it's 0 all the way to some critical value we call PC. And then from that point on, it goes up monotonically, as I said. And the way it departures from PC is very interesting. It's not with it's not smooth in any way. It's the function is supposed to be expected to be continuous. It's actually proved to be continuous by Harris and Kasten. But the first derivative is discontinuous. It's actually approaching infinity as we approach PC. It has this interesting shape. In fact, for this lattice specifically, PC is 1/2 by some beautiful symmetries. But there are still many questions, especially as we go beyond 2 dimensions. In 2 dimensions, the model is reasonably understood, especially if you go to the hexagonal lattice instead of the square lattice. We know that theta of PC is continuous in 2 dimensions, and in all dimensions bigger or equal to 11. So this interval between 3 and 10 is big. It's a big mystery from the mathematical perspective. Although we don't expect the hard problem to be the whole interval from 3 to 10. Actually, it's 3, 4, and 5, which are the tough cookies. 6, 7, 8, 10 are expected to be simpler. So this is an example of interesting questions that are left open. Also, how this theta behaves as you approach PC is an interesting problem, even in dimension 2, except for the hexagonal lattice. But we're not going to talk about this model specifically. We're going to make a modification to it. So, inspired by some questions in pure math and some modifications of some applied questions in percolation itself, we're going to present a model that I'm going to talk a bit more about the history later, but here is the definition of the model. We are not going to consider the square lattice per se. We're going to stretch it both horizontally and vertically. So you see that both in the X and Y axis, we're going to fix an IID sequence, psi I1 and psi I2. So these sequences are geometric row random variables. Here I fix geometric as being at least 1. So you can fix geometrics that take the value 0, but here is not the case. It's at least 1. And these variables are going to give the interspace between the columns. The other variables are going to give the interspace between the rows. So you see here, let me see, mouse pointer is showing. From this column to this column, we have what, 6, cycle 6. So that means for this edge, you can think of it as one edge that is very long, or you can think of it as 6 edges attached to each other. So in any way, to cross horizontally here, you don't have to pay P as usual, you have to pay P to the 6. So another way to define this model, which is fully equivalent, is to say that each column of vertical edges like this is going to toss a coin, and it's going to be deleted with probability 1 minus rho. So that's an equivalent definition of the model. So in any way, we have now a lattice that looks very similar to the square lattice, but the edges are harder to cross. But not only they're harder to cross, this hardness is kept along columns and rows. So there is some infinite dependence in this model.
So by the way, this is still in Z2. We are stretching Z2, right? Or yeah.
The whole talk is going to be focused on Z2. There are some very interesting questions as we increase the dimension. We don't know how to solve. So let's see a simulation of this thing. So here it is. It's a nice experiment to do mentally, to try to cross from left to right. This picture I chose the parameters and samples until I got a left, right, and top-down crossing, so you can find both. But it's not as easy as in the standard percolation. So usually in standard percolation, in the supercritical phase, right, where theta is positive, you can find very easily the crossings from left to right and top to bottom. Here, it's a bit harder, and actually there is a trick to find the crossing. You see that here, along this vertical part, there is a big gap, right? This column here is fully, it has a lot of things deleted. So you first find the crossing here. So this is going to be your bottleneck. And then you continue to left and to right. If you start from the beginning, you may end up, in a, here I was lucky, but you may end up in a dead end here and have to backtrack and so on. So first find the crossing in the hard columns or the hard rows, and then you continue them. And this is not only a trick to find these crossings, but also it's kind of part of the proof. So the difficult part should be treated first somehow. So this is a model that was first introduced by Jonasson, Mossel and Peres. So they treated a similar model that was actually easier in higher dimensions. And they felt, okay, this model is just slightly harder, it's in 2 dimensions, and they conjecture that for a small enough density of defects, so you don't expect the bad columns to be very wide, and for very large P, meaning after you done your deletion of columns, you do also a very mild deletion of edges, you should still see percolation, right? So imagine P rho is 10 to the minus 10 and P is 1 minus 10 to the minus 10. So you basically not delete anything. You should percolate. But it was actually a harder question to be solved. There was some progress by Bramson, Durrett, and Schoenman, where they only delete vertical rows. And they show exactly that. If you delete few of them or with small probability, and you keep P very close to 1, you still see percolation with positive probability. And then it took quite a while later for Hoffman to prove that you can do this both vertically and horizontally. We have a result with Marcelo, Marcos, and Remy showing an extension of this middle theorem here, where you allow the variables psi to have heavier tails, right? I said they're geometric. But if you only delete the vertical ones and you keep the horizontal ones in place, you can actually do much heavier tails than geometry. You just need 1 minus epsilon moment for the variable psi, and you still have percolation. So you can cross very big gaps. But as soon as you introduce the horizontal and vertical, it's more complicated, and you cannot do heavy tails. So Hoffman's proof was very interesting, very ingenious, and notoriously hard. And it was based in a dynamic renormalization. I'm going to explain soon what dynamic renormalization means in this context. And I'm going to present an alternative proof that is based on static renormalization. So it's basically inspired by Hoffman, but at least from my perspective, I find it simpler to follow. Okay, so I'm gonna rephrase a little bit the problem. You remember that in the first picture, I kept this dotted vertical and horizontal lines representing what was deleted. I'm gonna just show a Z2. We're gonna only deal with Z2, but these edges, they are harder or easier to cross depending on the variable's psi. That's basically equivalent. You put the xi's in the integers. Now to cross, for example, this horizontal edge, you have to pay P to the psi 1, 1. And to cross this vertical edge, you have to pay P to the psi 2, 2. Okay, so the psi's refer to the east or north edges corresponding to a site. Actually, sorry, I made a mistake. It's p to the xi plus 1. Yeah, maybe
So
not plus 1. Sorry.
are you allowed? But so your geometric
Yeah.
is minimum value of your geometric is 1, right? Or what is the convention?
Yeah,
maybe?
yeah.
Okay.
So it's not, this plus 1 is wrong. Either you someone here or you. Oh yeah, what I want to do, sorry, is to someone here and allow my geometric to be 0. Sorry. Yeah, that's important for the notation that comes. It's only to make the next notation correct. Okay, so the proof, you see that
so what is Xi again? In terms of the two geometries, what is Xi?
it's the geometric. Sorry, oh,
I
I forgot the upper script, yeah. So Xi is just a geometric. If it's horizontal, there should be a 1 upper script.
Oh, okay. Whatever is the corresponding one.
So you see that the model itself has two sources of randomness, right? We first choose the environment. We call this the environment, where we delete rows and columns, or just choose the size now. And then there's a second source of randomness, which is open and closing edges independently with this p to the xi plus 1. So these two sources of randomness is one of the things that make the renormalization more difficult. The reason being, we want to extract a lot of independence in the second step, right? Because in the second step, everything is IID. And in the first step, there is a lot of columnar and row dependence. So we don't want to mix these two. So we don't want to treat the annealed measure, right? The measure that does the two randomness at the same time. So what we want to do is to first treat the environment and then treat the percolation. That's why the proof has two steps. And these two steps, of course, have to talk to each other. And the way they talk to each other is like this. We're going to show that with high probability, our random environment, our xi's are good. And I'm going to define good soon. And then we're going to show that no matter what good environment you take, like the infimum over all the good environments, you still percolate with positive probability. So we have to have this notion of good that is not too strict, otherwise you can't show that it has good probability in the environment case, but it's not too relaxed, otherwise it doesn't percolate for the worst possible good environment. So you have to balance the notion of good that sits in between these two sources of randomness. And for this, we're going to employ a renormalization argument. So in renormalization, you have the typical idea is to take your lattice and consider it composed of big blocks. So instead of considering the sides of the lattice, you consider big boxes. And if you choose these boxes, looking at the randomness, right? You look at what's open, what's closed, and then you choose what the boxes are. This is what I call a dynamic randomization. It's harder to follow. Here we choose the boxes like this. They are fixed. They don't depend on the randomness. And for each k, each k of k, we are going to choose a paving of the line with boxes of size 500 to the k. So here you can see the typical interval. It's scale k, index j. It's just this formula here, but it's simple. It's just the jth interval counting from the origin that has length 500 to the k. And this choice is also convenient because a interval in the scale k is paved by exactly 500 intervals in the previous scale. So that fact that one is nested on the other will also be convenient for us. Okay, this slide is the only slide I don't expect to be fully understood because it's going to be explained later. But it's just to give a taste of what's going on. So if you have doubts about this slide, please ask, but it may be that I'm not able to explain right now. So in the environment case, we're going to give a defect probability to each interval. So we're going to say, okay, this interval, so it has defect H. We're going to give labels to intervals when we are treating the environment. And this label just says how bad it is. And we're going to keep track of the probability that an interval is H bad. And since these intervals are independent, right? Like this interval, this interval, this interval, they're independent. This, you expect the probability of having label H, and then the next to have label H2 to be multiplicative, right? So that's all I wanted to say, that the algebra that you expect in this part is a multiplicative algebra. Like the probabilities probably should look like something to the label, because then you're going to get an addition in the exponent. Now, after we labeled all the intervals, both horizontal and vertical, let's keep horizontal in mind for now. We're going to try to percolate. So that's the second phase. In the percolation, we're going to cross these bad columns, right? Just like I showed you in the simulation there. And we're going to do so with an army, what we call an army. We're going to just put a lot of sites here, and we are going to see how many survive after crossing the bad column. And you see that if you're crossing a column, and then you cross another column, and then you cross another column, the loss that you undergo is also multiplicative, or whatever is the analogous to divide. So you keep dividing your army as you cross bad columns. So these two play a similar role, and that's the heart of the proof, that you should multiply in the environment and divide in the percolation phase. It's actually silly, but it was what took us the longer to understand. So now let us try to make that slide a bit more rigorous. So we have an environment where we want to grade defects. So we want to give them a label H. So the interval that has scale K at position J is going to be associated with a label HJK. So now only the H equals 0 are considered good. So if you give label 0, that means, oh, this interval is good. It's going to actually help us instead of harming. Everything above 0 is bad, and we're going to have to lose armies in crossing those. So you expect H0 to be the typical thing. So we're going to define everything in this talk inductively, right? That's very common in multi-scale renormalization. We first say, okay, for the scale 0, what is the definition of defect? So first recalling, in the scale 0, our boxes, our intervals are unitary, so they're just single sites. Actually, I0j is just a site j. So we're going to give the label equal to the geometric random variable psi. Remember that in the end, we're going to choose the variable, the row very small, right? So that means most of the boxes in scale 0 are cycle 0, meaning H equals 0, so they're good. In the beginning, we have plenty of good boxes. Here and there, we're going to find cycles 2, cycles 3, but you expect them not to join forces to do something evil in a bigger scale. We expect actually to become easier and easier to be good as we grow the scales. So how do we define inductively? Suppose that you already know how to label boxes in a certain scale, you just want to know how to label them in the scale above. So as I said, something at scale k plus 1 is composed of 500 boxes at scale k. If all of those are good, we are done. The label is 0 for the big scale. There's no mystery, right? 0, 0, 0, 0 leads to 0 in the bigger scale. If they're not good, that means they have some H's there. And we're just going to sum the H's, right? So if a box is composed of, say, 003, 0005, 000, we're going to sum these and it's going to give us 8. Now, one exception, and it's a very important one, is when there is a single bad box. So if say 0003, 00000, then we are not going to copy this 3 to the scale above. We are going to actually subtract 1. It's kind of a healing effect. If you're alone, a bad box alone in a good box, in a big box, then the big box is likely better than you. Otherwise, it would be hopeless, right? Because if you're just summing things, imagine that you are dealing with a very large scale, the sum of things inside is going to be positive, right? It's very unlikely to be 0. But as soon as we put this healing effect, things tend to improve, which is not fully intuitive. But yeah. Is there any question? Okay, so now I'm going to give a brief sketch of why this heals and why things are typically good. What we actually prove is that the probability that a box at scale k is labeled with h decays both with k and with h. Here, maybe you have the feeling that it's exponential decay because things are in the exponent, but not actually, because remember this box is of exponential side length as well. So a box here has sides 500 to the k, so it's actually a polynomial decay. But it is a large degree, right? Degree 10 to the scale and degree 20 in the label. So we prove this. The proof is done by induction. In the 0 scale, it's just bounding a geometric random variable. It's here, it works. Now, as we go from one scale to the other, I'm going to give a broken proof for you here. What's the probability that at scale k plus 1, we have label h? So we sum over all possible values of the labels in the previous scale that sum up to h, right? So we take all the possible combinations in the previous scale that would give us h, and now we take the product. This product, you see, it's, there's a minus 10 to the k, minus 20 to the hi. That's the probability to have a defect in the hi by induction. So this product is going to become a sum in the exponent. So we're going to sum all the hi's, which give us h. Of course, I cheated here because there's an entropic factor, right? So where is all the possibility? If it was a single possibility for this to happen, this would be correct. But there is an entropic factor. And I'm cheating here. So the actual proof of the above lemma has to use the healing. Here I didn't use the healing at all, right? Just said, okay, sum over everything. So what we actually do is likely more subtle and takes into account the recovery, and it works. But the idea is basically that you just have a multiplicative thing in the defect. So that means you should be adding the labels. Questions? Okay, so if we accept this lemma with the broken proof, what's the probability that some box has a label bigger than 0? You have to sum over all the labels above 0, and that's still very small. It's still decaying with the scale. So the probability that a box is good is going to 1 very quickly as the scale grows. And that's what we're going to call the good environment. A good environment is an environment for which every interval containing the origin is good. That's all we ask.
So by the way, Augusto, just a small thing. So because of this presence of healing, I mean, it can be that but I think that will be very sparse. So the level is 0, but still you might have some, right? Which is big, some interval between, because you are subtracting 1, right, as you pass it over to the next step. In this case, when right? I mean, what I'm just saying is, go ahead, yeah.
So you could have an interval at scale like 500 to the 10, so at scale 10.
Mm-hmm.
And inside it, there could be something very bad. Like, for example, it could be that in the scale 1, there's a single site that has h equals 9, xi equals 9. So that's
Right.
going to be very hard to cross, but it's fully surrounded with good stuff.
Right. Mm-hmm. That's it. Mm-hmm.
Actually, it doesn't need to be that good. It could be that there's a site with 9, several sites with 8, several sites with 7, but they all are kind of far apart depending on the scale they are,
That's right. Mm-hmm. No, even when actually it is, let's say if it's 0, there can be several right, the situation at different scales where you could have one bad surrounded by all good, and right, and that bad means just one. Yeah. Mm-hmm.
Yeah, when you have a good scale, it has to be composed of a single interval with h equals 1.
At most, yeah, at the worst, that would be, yeah, this is the worst case, basically. Yeah. I mean, the best case is, of course, 1.
Yeah, this guy with h equals 1 has to be composed of a single guy with h equals 2. There's no other way.
That's true.
But now that guy has two choices. Either it has, so someone with h equals 2 can either have a single one with h equals 3 or two one with h equals 1. Just have to have options.
Right. Mm-hmm.
And so just to finish this, so if you have h equals 2, we have two choices. One of them is to have one site with h equals 3, but that's cost quite a bit because h equals 3 is costly. Or having two guys with h equals 1, but that also is multiplicative on the cost, so it's also not easy to do. Now we are going to the environment. We suppose that things are good in that sense, and we are never going to consider the geometric random variables anymore. Now it's like take the worst possible case, which is still good. And we're going to try to, don't read yet. We're going to try to cross a column, right? So we're going to put several sites here in the left and see how many are left in the right. So S is going to be our starting set, and it cannot be anything. For example, if S is very packed together, it's very easy to kill an expected number of people in the army. But if it's very packed together, it's kind of easy to surround this army. So what we expect is, what we require is that the army here is what we call a fractal set. So a K fractal set is, first of all, remember that we are trying to cross something bad here in the x-axis. But in the y-axis, there is also a notion of good and bad. So what we require is that S lies in a good interval in the scale K. So we cannot position our army in a bad row. Otherwise, it becomes harmed by the horizontal problems. So we want them to be in a good interval. And this K fractal set is composed of a union of K minus 1 fractal sets. How many of them? 16. That's all. So if we take a disjoint union of K minus 1 fractal sets, we get, of 16 of them, we get a K fractal set. And with this notion of what is considered a good set to cross this column, we're going to define the quantity that we want to bound. So take any bad interval you want. Now you take any K fractal set that has size. Oh, sorry. This is not ideal because the K fractal set here has fixed size. But what you have to see is that 2 to the 4k is the size of the K fractal set. So you have to take 2 to the hk of them. So S is composed of many K fractal sets and the size in the end is this. So you see that it needs a bigger army if you're going to cross a harder trap, right? And it's multiplicative. And V asks, what's the probability that you don't end up with a big army after all? And big meaning proportional to the, like a polynomial in the size of what you crossed. You see, so that's the quantity that takes some time to massage, but it behaves very well with these multiplicative things we are analyzing. Take the worst possible trap, take the worst possible K fractal set here. What's the probability that you don't end up with a sizable army in the right? And you're gonna bound this variable and it's gonna give us everything. Observe that we don't restrict the vertical space. We are crossing something of scale K, but we could utilize something much larger vertically. And that's important because of what it's going to be clear why it's important that we don't restrict the vertical positioning of the army. It could be very sparse going up and beyond. So first, so we prove a lemma that this decays, just like we proved that the probability of labels decay in the environment. Here we prove that probability of V also decays if P is close enough to 1. So first of all, if we prove this, we are done. I'm not going to give the details here, but if you can cross something with all these things and the environment is good, we basically just start to make it's like a staircase where we do something here, something thicker up, something thicker left, something thicker up, and we just go to infinity with probabilities that sum. So we can use Borel-Cantelli. That's a very used trick in percolation. Once you get the right event decaying, the right definition of bad event decaying, we just make some geometric construction that Borel-Cantelli shows there is percolation. So I'm not going to do this geometric construction, but I'm claiming that it's enough. The way we prove this is as everything is talked by induction in K. So how does that VK look like at scale 0, right? At scale 0, you're trying to cross a single site. The column that you're trying to cross is a single site with a single edge. So basically, you start with your army. It has size known, and it has, so it's basically binomial. The size of the army gives the number of the n in the binomial, and the psi gives the p to the binomial. And it's a simple concentration on the binomial that gets you this. Binomials concentrate, so this works. Now, the induction is harder, and it's gonna be exactly where we are gonna use the recovery. So this is kind of philosophical somehow. In the first step, when we did the environment, there was environments that had several traps and environments that had a single trap, and we treated them differently. Unavoidably, we're gonna have to now treat them differently as well. That's life. So I'm just gonna show one picture for each, and the proof is finished. So this is the case where you have several traps. So I'm just showing 2 here, but the argument is similar for as many bad columns you have. So we're trying to cross something of scale K plus 1. It's composed of 500 things at scale K. And I'm here drawing the case where 2 of those are bad. The rest is 0. So the 0 things we cross easily. We don't lose anything, basically, when you're crossing good stuff. So that's why we start with a size 4K plus H, and we end here right before the trap with also 4K plus H. But remember, H is H1 plus H2. And we cross the first trap, and what the induction tells us is that we lose H1. So we end up with an army of size 2 to the 4K plus H2. it doesn't get harmed walking in the good part. And then you cross the bad thing, you lose the H2, and you are left with 2 to the 4k, and you cross the good things without losing anything. So you see that exactly the successive crossings of bad things, taking you exactly their label in the exponent, is the induction. Why did I say it's different in the case of a single trap? So if you have a single trap, let's recall what we are doing. We're crossing something of scale k plus 1 that was labeled h. So we start with an army 2 to the 4k plus h that we can keep all the way to the neighborhood of the trap. But now the problem is, in the environment analysis, we had to introduce some healing. Otherwise, you'll never make the first part of the proof work. So that means this trap is not h. It's actually h plus 1. It's going to be harder to cross this. Once we cross it, we are left with something that is not sufficient. We claim that we will be ending this with 2 to the 4k, not 2 to the 4k minus 1. So what we have to do is some healing also in the environment to show that the healing we did to ease our lives in the first part of the proof can be compensated. So there are actually two cases. Here I'm showing the easiest case, which is after you cross, you heal and you go back to the right size. But if this trap is too close to the right, you have to heal before hitting the trap. So you increase your army before you reach the trap, because you have space in the left, right? If the trap is too much to the right, you have space in the left. So you heal before and then you cross. And that's it. I'm hiding details, of course, but I think the proof is much more understandable after this massaging we did. What are the takeaways? So something that I always like to say when I present something about renormalization is that, okay, renormalization has a bad reputation of being cryptic to read. And I try my best not to write papers in a way that it's cryptic, and I try to emphasize the storytelling. I learned most of renormalization in the beginning of my master's with Vladas Dravicius, and he was always emphasizing that renormalization has some storytelling. So good things, bad things, hard regions, your army dies. In this kind of situations where we have two sources of randomness, we have to make an agreement, like a contract between the two parts of the proof. And the contract is what you consider to be good enough for the first part. And there was an algebraic interplay between these two, which is very nice. I mean, it's an overkill to call this algebraic interplay because just products and sums in the exponents. But anyway, and I think from now there are several things that this can be applied, this quenched type of renormalization. So I'm listing here the high dimensional case that Shwajit already asked. The Cox process is something that's quite mysterious for us. And we can add dependence there and see how this survives or not, these strategies. But that's it.
So what part of the story would not work if you, let's say, just added one more dimension? And so what part will run into trouble?
So when you add one more dimensions, you have to, so sometimes you add one dimension makes things easier. Just like percolation, when you show that you percolate in the plane, so you also percolate in Z3, right? So yeah, sometimes you make it easier. The way you can make it harder is, for example, I'll give two examples that are of very different natures. So the first one is try to find a random surface. Instead of random path, a random surface that only crosses, let's say, a Lipschitz function whose graph is only touching good sites. Right? This has been studied by Grimet quite a bit in the IID case. But now if you if you put these stretched defects, these columnar defects, everything breaks. You have to deal with two sources of randomness and this infinite dependence. Another thing you can do is to look at kind of the other way around. Imagine that you have the contact process in the plane, right? It survives because even in the line it survives, so in the plane it survives even more. And now you even add some sites. Every site has a geometric random variable, and if the geometric is large, it makes it harder for the site to heal. It's like how susceptible this site is to the infection. So now it's surviving even more. Can you show that this process dies for low enough contagion rate? So that's the same idea of the Lipschitz function. It's another high dimension. You have to show that it dies, right? So you have to show that a surface of death is kind of covering the plane.
All right. Thanks. Yeah.
And I'll end with a quote by Vladas Zoravicius. So he asked this several times to me during the masters, and I really like this provocation. He asked, what's a sequence of IID random variables, right? Of course, everyone knows what a sequence of IID random variables, but when you start to try to represent it deterministically, there are several ways, right? You can say, let's say a sequence of coin tosses. It's something that has no more than 2/3 of heads. That's a deterministic way to say that an infinite sequence of Bernoulli coin tosses is, right? It's just a sequence of zeros and ones that doesn't have more than 2/3 of ones. Of course, that's one way to see. Another way to see is like, maybe you have 0, 0, 0, 0, 1, 0, 0, 0, 1, and these ones come with density half. But maybe you have 2 ones in a row. Oh, this happened at rate 1/4. And then you have sometimes 3 in a row. That happens in periods of 1/8. This is actually very related to the proof by Hoffman. He first starts with a deterministic sequence that has these periods, right? Every 1/p sites, it has a dot. Every 1/p square, it has 2 dots, and so on. And he first proves that this environment is good and survives, and so on. And then he goes to the Bernoulli. So there are several ways to describe a Bernoulli sequence of random variables in a deterministic way, and sometimes they are enough to prove stuff about Bernoulli, sometimes not. And here's 2 nice pictures. In the seminar website, there was this beautiful painting. Since I'm in Portugal, I decided to add some Portuguese styles as well. Thank you very much.
Thanks, Augusto. Any questions? Okay, I think I'll ask one. So how it needs to be modified when you want to incorporate the heavy tail for just in one-dimensional stretching, one direction?
So in one-dimensional, when you're just
vertical or horizontal, right?
Horizontally.
Yeah.
And you add the
now that you said, right? You just need a 1 minus epsilon moment condition.
Exactly. And then the proof is completely different. It doesn't use these armies or anything. It was actually what we proved before, and we were expecting that proof to extend to the 2 defects, but it doesn't. The proof, you see, it has to use much more vertical space. So if you have a defect that is the heavy tail, then it's going to find some trap that you have to go up like exponential of square root of t to cross it, right? So if you want to walk t steps to the right, you usually have to move exponential of square root of t vertically to find the exits. So this is quite intense, and the
see.
proof has to change completely because of that.
I see. Yeah, that's really interesting. And I think, well, you already said this, but just adding one more dimension also changes the picture completely. So probably it's far away, but let me ask anyway. So, you can potentially ask the same questions, let's say on Kelly graphs of groups, right? You, let's say, have some finite generators and, probably, it's basically, you can essentially make similarly sense of that, but again, that would be even actually more.
Yeah, that's interesting, because as soon as you leave the Euclidean space, it's hard to tell what a columnar defect is, right? But if you're in a group, it makes sense, because just take.
Yes, that's what I was saying. Groups, yeah, you can.
Group, yeah.
But even adding one dimension, actually seeing, understanding the thing, and then I'm less sympathetic about that. But no, this is really great.
At the same time, for groups, I think the first group that comes to mind that is not, that's interesting and doesn't contain Z2 is, I know the Heidelberg group maybe is the first interesting thing to play with. It's already a bit complicated, but
Right.
yeah, maybe.
It's great. Yeah. No, it's wonderful. Talk was also very instructive. So okay, let's thank Augusto again for this wonderful talk and wonderful afternoon. Thanks, Augusto.
Thank you.
Yeah,
I'll write to you. We're gonna have a lot to talk.
Yes, we have a lot to talk. Just we'll do that.
Write to you this evening.
Yeah. Okay. I'm looking forward to that. Okay, Augusto. Thanks a lot. Have a good day. Yeah.
Thank you for the invitation.
Your refreshment, your refreshment into waiting was probably whenever you visit Mumbai and give it to you. Okay. See you, Augusto. Talk to you.
See you,
Bye.
bye-bye.
Bye, Augusto.